Good afternoon, class. We are looking at Chapter 2, Limits. Here's Section 2.2, Limits of Functions at Infinity. So we covered 2.1, Limits of Sequences, and now 2.2, Limits of Functions at Infinity. So here's the synopsis of what we have already covered. Recall. A sequence is an ordered list of numbers or a function f whose domain is the set of natural numbers 1, 2, 3 to infinity. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. The limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. The limit of a sub n as n approaches infinity is infinity or negative infinity or DNE does not exist. We say the sequence diverges. To find limits, simply plug in and observe. Plug in the value. Let's look at a couple of theorems. The limit of r to the power of n as n approaches infinity is 0. If r is between 0 and 1, or more generally between negative 1 and 1, it's 1 if r is 1, and it's infinity if r is larger than 1. The limit of 1 over n to the power of p as n approaches infinity is 0 for p, the exponent larger than 0. Geometric sequence becomes a geometric series when we add them up. So S represents the sum, S sub n, summation of ar to the power of n minus 1 from 1 to n. This is the sigma summation sign. A plus ar plus ar squared all the way to the n. And we have shown that it's a times 1 minus r to the power of n over 1 minus r. If r is between negative 1 and 1, then r to the power of n goes to 0. And therefore, the sum becomes a over 1 minus r. B sub n plus 1 is r b sub n, and the solution b sub n equals b sub 0 r to the power of n, or a instead of b sub 0, depending on the text. This is the geometric sequence recursively, and this is explicitly. That's the solution. If we add a constant to that, like giving medications to patients, then this value will add this part c times 1 minus r to the power of n over 1 minus r. Again, in some texts we use a, in some texts we just use b sub 0. I want to make sure everybody's comfortable with that. And now we're going to go to section 2.2, limits of functions at infinity. Here's the summary, the definition. Horizontal asymptote short HA of the curve y equals f of x is the line y equals L if the limit of f of x as x approaches negative infinity is L, or limit of f of x as x approaches positive infinity is L. Now, limit of 1 over x as x approaches infinity is 0. The limit of 1 over x to the power of p as x approaches infinity is 0 if p is larger than 0, which means y equals 0 becomes the asymptote. Now, a couple of functions we are familiar with. One of them is an exponential function, y equals b to the power of x. If b is larger than 1, we are dealing with an exponential growth. If b is between 0 and 1, it's an exponential decay. And therefore, an example of an exponential growth is y equals e to the power of x. The limit of e to the power of x as x approaches negative infinity is 0. That's the x-axis, and that gives rise to the horizontal asymptote y equal to 0. The limit of f of x as x approaches infinity is infinity. It's referring to the first quadrant. When b is between 0 and 1 and it's a decay, limit of f of x as x approaches minus infinity is infinity. It refers to the second quadrant. The limit of e to the power of minus x, as an example, y equals e to the power minus x, is an exponential decay. As x approaches infinity is 0, and in both cases, you see that HA, or horizontal asymptote, has the equation y equals 0. Okay. One of the functions we are all familiar with is y equals x cubed. And what do we know about y equals x cubed? The limit of f of x as x approaches negative infinity is negative infinity. That means the third quadrant. And the limit of f of x as x approaches positive infinity is infinity. That means the first quadrant. And as you recall, this is known as the end behavior. Now, let's look at this example. We want to find the limit of 3x squared minus x minus 2 over 5x squared plus 4x plus 1 as x approaches infinity. And as you recall, when we have a rational expression and x is approaching infinity, we divide by highest degree term in the denominator, namely x squared. And we are going to make up three fractions here, 3x squared over x squared minus x over x squared minus 2 over x squared, and we're going to do the same thing to the denominator. Applying the limit laws, we're going to apply the limit to the top and the bottom. Continuing with the limit laws, we're going to apply the limit to each term in the numerator as well as each term in the denominator. And now, this is a constant, the answer is 3. This is a constant, the answer is 5. And this one, this one, this one, and this one, each one, the denominator goes to infinity, therefore becomes 0. And if you show work and from here you go to this step, in other words, you skip this two, I'm okay with that. The answer is 3 over 5. So if we look at the graph of the function, okay, y equals 3x squared minus x minus 2, here's the function, over 5x squared plus 4x plus 1. Y equals 3 over 5 is the equation of a horizontal asymptote as x approaches infinity gets there. What about here? The limit of f of x as x approaches negative infinity is also 3 over 5. First of all, the methodology is the same as this one. You divide by x squared if x approaches negative infinity. Secondly, it crosses the horizontal asymptote and it runs along that as it approaches negative infinity. Okay. Infinite limits at infinity. The notation limit of f of x as x approaches infinity equals infinity is used to indicate that the values of f of x become large as x becomes large. Similar meanings are attached to the following symbols. Limit of f of x as x approaches negative infinity is infinity. Limit of f of x as x approaches infinity is negative infinity, and limit of f of x as x approaches negative infinity is negative infinity. All of which refer to what we learned in algebra as the end behavior. By end, it means what happens when the x approaches either positive or negative infinity. So having said that, some of the functions we are familiar with. Y equals ln x, y equals square root of x, y equals x squared, y equals e to the power of x. All of these functions, first quadrant, the limit of f of x as x approaches infinity is infinity, first quadrant. On the other hand, reminding you again about y equals x cubed, the cube function, the end behavior. The limit of f of x as x approaches infinity is infinity, first quadrant. The limit of f of x as x approaches negative infinity is negative infinity, the third quadrant. So, in short, when you take a limit of the function as x approaches either positive or negative infinity, we mean the concept known as the end behavior. To find the limit, just plug in and observe. So what happens? Well, we may get to a number. We are done. Any number, we're done. The limit of f of x as x approaches a is some number. Or the limit of f of x as x approaches a is 0 over some number. By some number, we mean anything other than 0, and the answer is 0. The limit of f of x as x approaches 0, if it's some number over 0, it might be infinity or negative infinity. And why is that? The number in the numerator is either positive or negative. But 0, as we approach it from the left, is negative, from the right is positive, so it could be either one. And I'll show you how we approach it as we come across an example. Finally, most of the time in calculus, we end up with indeterminate forms. Examples, limit of f of x as x approaches a is 0 over 0, infinity over infinity, infinity minus infinity. It doesn't mean that we have a definite answer here. It means it's indeterminate. We have to use our algebraic techniques to figure out what the answer is. The limit of 5t plus 7 over t squared plus 2t minus 1 as t approaches infinity. First of all, if you plug in, you get 5 times infinity plus 7 is infinity. Infinity squared plus 2 times infinity minus 1 is infinity. You get infinity over infinity. However, because it's a rational expression, and t is approaching infinity, you divide by highest degree term in the denominator. That is always the technique. And so when you go through the process, this becomes 5 over t. This becomes 7 over t squared. This becomes 1. This becomes 2 over t. This becomes negative 1 over t squared. And since t is approaching infinity, everything goes to 0 except 1. And 0 over 1 equals 0. What about this one? Same manner. First of all, if you plug in, you get infinity over infinity. Secondly, you're dealing with a rational expression. T is approaching infinity. The technique is to divide by t. So we're going to divide by t, and we're going to simplify. So we simplify each fraction. We end up with the limit as t approaches infinity of t plus 2 plus 7 over t over 5 plus 7 over t. We are going to replace the t. We get infinity here, 2 here, 0, 5, 0 here. So the numerator is infinity plus 2 or 2,000 or minus 10,000 makes no difference. Divided by 5 or 5 billion makes no difference. The answer is infinity. The only thing you want to be careful of, if you're dividing by negative, the answer is negative infinity. Now, you may have seen this before. Because the degree of the numerator is less than the degree of the denominator, you get 0. Because the degree of the numerator is larger than the degree of the denominator, you get infinity. If the degree of the top and the bottom are the same, just the leading coefficients take over, as it was the case. The very first example we did, the first example we got 3/5, the coefficients, okay, the leading coefficients. Now, if you want to go that route, you have to mention the degree and you have to mention what the degree is. For example, you have to mention the degree for the numerator is 1, the degree for the denominator is 2, and that may be acceptable. In this case, the degree for the numerator is 2, the bottom is 1, and it's larger, and therefore it goes to infinity. But this is the more proper way of doing it, okay, as far as calculus is concerned. Now, what about the limit of square root of x squared plus 1 minus x? If we plug in, this is infinity squared plus 1, which is infinity. When you take a square root of infinity, also is infinity. And remember, infinity is a concept. So you plug in, you get infinity minus infinity. So what's the technique? Whenever you have a square root, the technique is to multiply by a conjugate. The conjugate for a minus b is a plus b. Their product is a squared minus b squared. So the conjugate for this, you write the same thing and you change the negative to positive. And why do you multiply by the conjugate? Because you're going to square the first one minus the second one, it comes out. But you can't just multiply by it. You have to also divide by it, because this expression that you're multiplying by must be equal to 1. You can't just multiply by anything. So if you look at the numerator, the denominator remains unchanged. The numerator is the product of these two, which is the first piece. That means square root of x squared plus 1 quantity squared minus the second piece, that means x squared. So the first piece comes out. These two cancel each other. And now, if you plug in everybody, this becomes infinity, this becomes infinity, and the answer is 0. So you're justifying your answer with details. The limit of 12/4 plus 3 e to the power minus t as t approaches infinity, just plug in. And if you plug in, you get 0 here. Why is that? Reminding you, the negative exponential rule says a to the power minus m is 1 over a to the power of m. Therefore, e to the power minus t is 1 over e to the power of t. And so this one, e to the power of minus t is 1 over e to the power of t, or 1 over e to the power of infinity, or 1 over infinity, or 0. And so 12/4, or 3. What about this limit? The limit of 5 plus e to the power of t over 4 minus 3 e to the power of t as t approaches infinity. If you plug in, this becomes infinity, this becomes negative infinity because of this negative 3. This is not a rational expression, because rational means the top and the bottom must be polynomial. Okay, they are not. They are called transcendental functions. But the technique is the same. Because t is approaching infinity, you divide by highest value in the denominator, which is e to the power of t. And you simplify. This becomes 1, this becomes negative 3. The other two remain unchanged. So because t is approaching infinity, 5 over e to the power of infinity, this goes to 0, this goes to 0. The answer is positive 1 over negative 3, which is negative 1/3. What about the limit of x squared minus x as x approaches infinity? You plug in, you get infinity squared minus infinity, which is simply infinity minus infinity, and it's indeterminate. So what is the technique here? You notice you can factor. So we are going to factor the x out. The limit of x times x minus 1 as x approaches infinity. It's infinity times infinity minus 1, which is, of course, infinity. As you recall, the previous example on the previous page, we ended up with infinity minus infinity, that the final result was 0. Now infinity minus infinity, the final result is infinity. That's why it's called indeterminate. We don't know what the answer is until we use our algebraic techniques and check it out further. All right, this is a rational expression, the limit of x squared plus x over 3 minus x as x approaches infinity. Because it's a rational expression, and because x is approaching infinity, the technique is to divide by highest degree term in the denominator. So we are going to divide everything by x. And by the way, if you plug in, of course, you get infinity from the top, and the bottom is infinity. This negative makes it negative. So divide by x and simplify. So this becomes x, this becomes 1, this becomes 3 over x, this becomes minus 1. So you divide and you simplify. When you do so, plug in and you get infinity plus 1. Plug in, you get 0 minus 1. And this is what matters. The top is infinity, infinity plus 1 or minus 1 or any number, doesn't matter, infinity. Because the bottom is negative, the answer is negative infinity. That's what I want you to be careful of. Okay. Also, if you want to go back to what we learned previously, if you want to look at this and say, okay, the degree of the numerator is larger than the degree of the denominator and it goes to infinity, there are two things you want to pay attention to. Number one, you want to mention the degree of the numerator is 2 and it's larger than the degree of the denominator 1. Therefore, the answer goes to infinity. And you want to be careful because of this, it ends up being negative infinity. That's why if you just go with the degrees, you may answer infinity, whereas this one is really negative infinity. So you want to be careful with that. Example 4, the Pacific halibut fishery has been modeled by equation B of t equals 8 times 10 to the power of 7 over 1 plus 3 e to the power minus 0.71 t, where B of t is the biomass, the total mass of the members of population in kilograms at time t. What is the limit of B of t as t approaches infinity? Just take a limit. Limit of B of t as t approaches infinity is limit of 8 times 10 to the power of 7 over 1 plus 3 e to the power minus 0.71 t as t approaches infinity. Anybody can see the answer? I'm sorry, I couldn't hear you. One more time, please.
Yes.
What's the answer?
The 8 times 10 to the power 7 over 1
Perfect.
plus um
Perfect. Excellent. Excellent. And here's what happens, everybody. You apply t approaching infinity, and this becomes 0. Why is this 0? Reminding you again, a to the power of minus m, the negative exponential rule says it's 1 over a to the power of m. Therefore, e to the power of negative t is 1 over e to the power of t. So e to the power of negative 0.71t is 1 over e to the power of 0.71t. This goes to 0. And therefore, the answer is 8 times 10 to the power of 7. And same unit, kilograms. That's the biomass. What is the significance of this limit? In a long run, the Pacific halibut biomass will be 8 times 10 to the power of 7 kilograms. That means 8 with 7 zeros. That means 80 million kilograms. That's the meaning of it. All right, let's look at this example, everybody. A tank contains 5,000 liters of pure water. Brine that contains 30 grams of salt per liter of brine is being pumped into a tank at a rate of 25 liters per minute. Show that the concentration of salt after t minutes in grams per liter is B of t equals 30t over 200 plus t. So the first part is algebra. We want to show that this is a correct statement, expression in essence. So to do so, first and foremost, the concept of a concentration of salt, that means the amount of salt over the amount of total liquid. That's the meaning of it, and we're going to discuss that. We know that brine contains 30 grams of salt per liter. That means 1 liter of brine has 30 grams. And we are pumping into the tank at a rate of 25 liters per minute. So we are adding 25 liters per minute of brine to the tank. So we are adding this much, 25 liters per minute is being added. So to understand what's happening, I want to make up a table with the time, the amount of brine, salt, and so forth. So just for the sake of argument, 25 liters per minute. So just for 1 minute, that means we are adding 25 liters of brine. And if each liter has 30 grams, that means we are adding 25 times 1 times 30 grams of salt. So for 1 minute, we have 25 times 1 liters of brine, 25 times 1, 30 grams of salt. Just to make sure we understand this, let's say what happens after 2 minutes. 2 minutes means 25 times 2, 25 times 2 times 30. That's what it means. We just want to make sure absolutely everybody understands. Let's say 10 minutes. So if it's 10 minutes and it's 25 liters per minute, so 25 times 10 liters of brine, and then 25 times 10 liters of brine, each one gives us 30 grams times 30 grams of salt. But that's not what we are doing. What are we doing? Show that the concentration of salt after what? T minutes, not 1, not 2, not T, 10, T minutes. So replace the 10, 1, 2, 10 with 10, T. If I put a T here, this 10 and this 10 will replace with T, which means after T minutes, the amount of brine is 25 times T liters that is being added. Because 1 liter of brine gives us 30 grams of salt, after T minutes, we have 25 times T times 30 grams of salt added. That's understanding exactly what's happening here. So the total amount of salt that is being added is this, which means 25 times 30, 750 T grams. Total amount of liquid. This is the amount that has been added to what we had in the first place, 5,000 liters of pure water. So we've added this much, and that is the total liters. So we are going to go to this fraction. Salt in grams is this. Liquid in liters is this. We notice the top and the bottom are both divisible by number 25. So if we take out the 25 from here, this is 25 times 30. We already have that 25 times 30. Okay. This one divided by 25 is 200. This one becomes just T. And now we drop the common factor of 25. We are left with 32 over 200 plus T. And we just proved that the expression is absolutely correct. That's all we did. We just showed that the expression is correct, everybody. So now we want the limit. What happens as T approaches infinity? That means find the limit. Anybody can come up with the limit for us? Well, we have a rational expression, and T is approaching infinity. The technique is to divide by highest degree term in the denominator, namely T, and simplify. Everything is being divided by T. This is 30. This is 200 over T. This is 1. Because T is approaching infinity, this goes to 0. And the answer is 30 grams per liter. 30 grams per liter. A couple of things. Number one, we go back to this. You know the degree of the numerator is 1. The degree of the denominator is 1. So 30 over 1. That's one easy way, but you have to explain that. But what's happening here? Brine that contains 30 grams of salt per liter of brine, and we got 30. In a long run, all the liquid turn into brine. Why is that? That's the meaning of this limit. But why is that? We had 5,000 liters of pure water. Well, if you add brine, okay, 25 liters per minute indefinitely, and you do not stop, eventually the amount of water, doesn't matter 5,000 or 50,000, in a matter of comparison, in a limit sense, it is nothing. Therefore, the final result will become just like pure brine, and therefore it contains 30 grams of salt per liter of the total liquid.